Any questions so far? Okay, so let's carry on to number 4. So the number 4 is observables and operators, okay? So, once we are given a system, we can ask what are the possible experiments that we can perform on a quantum mechanical system, and what observables do they yield, right? So, what can we observe? And in answering this question, classical physics, we use a lot of intuition from classical physics. It turns out that quantum mechanics has certain observables which do not have any strict, like 100% analogs in classical physics. But, in this course, we will probably not get into those observables. So historically, of course, we follow our nose and develop quantum mechanics using classical physics. So, so the answers could be, say, the position of a particle, right? Because, and that is something that we can actually experimentally verify. So suppose that we have a screen here, or a Geiger-Müller counter, and it captures, say, a photon, right? So the particle at that point, at the moment of capture, had a particular position. So even if the position is not 100% localized, there is a sense in which position is an observable. Similarly, we can say momentum is an observable. For example, if I think about the Compton scattering experiment, there, momentum played an important role. So momentum could be another observable. And then, energy of a particle is another obvious observable. But we saw that, okay. Yeah. The other thing we expect is that, the result of measurement of an observable should be a real number, right? For example, if I measure the energy of a particle and find that it's a complex number, it would not have any interpretation. So energy can be negative, as we know. For example, for bound systems, if we say that the potential energy at infinity is 0, then, or at some point is 0, then we can easily have interpretation of energy having negative values. And kinetic energy is always positive, but having a complex value of the energy doesn't make sense. So and similarly for positions, similarly for momentum. So we require that the result of measurement of an observable should be a real number. But we saw that observables are abstract in the sense that they can be operators or differential operators, right? For example, we saw that momentum the momentum operator was given by h bar by I, the gradient operator, right? And here we see that, there is I prominent in this expression. So it's far from clear that operators in general will yield observables which are real numbers. So the question is, how do we get, real numbers from operators, which are complex. And the easiest way to solve this is to require them to be Hermitian in the finite dimensional case and self-adjoint in the infinite dimensional. So, okay, so if we require, say, operators to be self-adjoint, then their eigenvalues and consequently their expectation values, that is the average, my handwriting is not doing so well today. Their average value will be real. Okay, so what does it mean for an operator to be self-adjoint? It means that if I take any two states, say psi and phi, and calculate this inner product, and then take its complex conjugate, then this will be given by this. Okay, so for all psi and phi. And where did we get this? We got this from, we generalized the idea of a Hermitian matrix to a Hermitian operator. And then we required them to be self-adjoint. So, for example, this is self-adjoint. So this is what it means to be self-adjoint. So big self-adjoint implies that the operator O is Hermitian, meaning that if I take the matrix element of the operator, say XX prime, if I take the, Hermitian conjugate of the operator and its XX prime matrix element, then by definition, this is equal to star X prime X. But the operator being Hermitian means that this has to be equal to O dagger XX prime, okay? So this is what it means for an operator to be Hermitian. That is, this thing must be equal to that thing. Okay? Okay, so we saw in a previous lecture that when an operator is Hermitian, its eigenvalues are real. Okay, any questions?
I have a question. So, in physics 113, waves, we encountered like a complex representation of index of refraction and wave vectors, where the imaginary part would capture the idea of the attenuation of the wave.
Exactly.
So there was an interpretation of complex numbers even in classical mechanics. I'm assuming that is classical mechanics. So
Yes.
in this case, why are we assuming that the complex numbers wouldn't have an interpretation? Or like, how do we know that only real numbers would work?
Yes, that's a very good question. So in classical mechanics, whenever you use complex numbers, that has to do with the fact that if you take a wave equation, say a second order, an oscillatory system, potentially oscillatory systems. So essentially, if you have a linear system with some, some damping, then it um, admits two classes of solutions. One class of solution is the oscillatory solution, and another class of solution are the exponentially damped or the exponentially increasing solutions. And there is a parameter in those systems which controls whether you are on the oscillatory regime or you're on the damped regime, or if you're in the critical regime, which is often called critically damped. Okay, so in that case, we know that whenever we have wave phenomena, the complex, because of Euler's formula, the e to the power I kx, the exponential function, is a very useful tool that helps us solve those wave equations. But in classical physics, you actually don't need to use them. That's the idea. Okay? You don't need to use them. You could have, if you wanted, you could have done the whole thing using, say, just sine or cosine. So what would happen if you go to a regime where there is some sort of attenuation is that those sine functions and the cosine functions will become replaced by something exponentially decaying, and those functions can be expressed in terms of the Cauchy-Sinch functions, okay, which are related to the exponentially decaying and the exponentially, and as you know that by analytic continuation, you can go from the sine and the cosine function to the Cauchy and the sine hyperbolic functions, right? So, so just as in the case of oscillatory phenomena, we can use the exponential complex numbers as a convenient tool to express oscillations. We can also use the exponential as a convenient tool, or with its connection to say sinh and sine, hyperbolic, and cosine. Those things are kind of interchangeable. So what you're seeing in classical physics is a very, very is a technical. It's a convenience. It is not essential. Everything you do in classical physics, where you have some attenuation and stuff like that, you can still do avoiding complex numbers. It just becomes a little bit more cumbersome. Okay, so it's not true that in classical physics, we are using, that you have to use complex numbers to describe attenuation. I know what you mean, like the skin depth and stuff like that, right? That's when you have, when electromagnetic wave goes inside, inside a metallic or a medium where there is some kind of skin depth, right? And that's very easily expressed by having a complex index of refraction, right? But the point is you didn't need that. So the complex index of refraction is actually going to be something which has which could have been explained in a more less effective manner, cost-effective manner. But the complex numbers are just like, they're just very, very convenient. But there is nothing in electrodynamics which says that the Maxwell's equations must be expressed as a complex set of equations. You can, I mean, so for example, circular polarization is a good example. Circular polarization is very convenient to express them in terms of complex amplitudes, right? And that's because, circular polarization means that you have some, electromagnetic wave vector, which is, going around in a circle. And you know that, this is very easy to express using, the Euler formula, right? But that doesn't mean that, we cannot express it in terms of real numbers. We can. It's just that it's a convenient notation. And that's why, if electrical engineers are always using complex notation in circuitry. They're even like, they even came up with impedance, which is a complex, quantity. So you might say, oh, impedance is a complex observable. But the thing is, it's a convenience, not a necessity. Okay.
Yeah, that makes sense.
But you raise an important point because, when we observe, actually, I'll come back to it at the end of this point, okay? So let me just recap what I said. Hermitian operators, Hermitian, and by extension, self-adjoint operators, have real eigenvalues, okay? And we will see that one of the postulates of quantum mechanics is that when we make an observation, the result must be a eigenvalue of the corresponding Hermitian operators.